Right. So thanks a lot for the invitation, Pedro, and also for the introduction. So I am Roberto Verdel, and like Pedro said, I'm now in the Max Planck Institute for the Physics of Complex Systems in Dresden, in Germany. And today I want to present you part of the work that I've been doing over the last couple of years as part of my PhD. And in particular, it's a method for computing quantum dynamics, which we call variational classical networks. And before I begin, I'd like to acknowledge my collaborators for this project. So Markus Schmidt, who is now a postdoc in the University of Cologne, Yiping Wang, who recently moved to the National Tsinghua University in Taiwan, Peter Karpov, who is still a postdoc in our group in the Max Planck Institute, and Markus Heil, who is the group leader also in the Max Planck Institute. I think the camera switched off, but I don't know if that's normal while presenting. Otherwise, I will just continue.
Yeah, it should be all right.
Okay, perfect. All right, so let me already show you the outline of the talk. I'll basically discuss three main points. I'll start with a short kind of introduction to non-equilibrium quantum dynamics. Then I will discuss a possible solution to these problems regarding quantum many-body dynamics, which is that of variational classical networks. And finally, I will apply this method to a two-dimensional lattice gauge theory that, of course, I will introduce later on. And in particular, we were able to access the non-equilibrium dynamics of such a theory, and we were able to identify some sort of non-ergodic behavior, which is due to a mechanism that is known as disorder-free localization. And I will also explain what that means. So let me get started. I think I don't need to convince you about the fact that non-equilibrium processes are present everywhere and that they might be super interesting and important for many reasons. And that's particularly true in the quantum realm. And here I'm just showing you a couple of examples of interesting out of equilibrium quantum phenomena. So for example, on the left-hand side, this is like an artistic representation of a discrete time crystal, which refers to discrete time translational symmetry breaking, which might occur in periodically driven systems, also known as Floquet systems, in the presence of many-body localization. So what is important about this example is that it's a phase of matter that is intrinsically out of equilibrium. So there is no equilibrium counterpart for that. Another example, more from the community of high-energy physics, is that of string breaking, where, for example, you could have a pair quark-antiquark forming a meson due to the nature of the strong interaction, which is such that the interaction potential between these particles rises linearly with the distance. So as you try to pull them apart, basically the energy of doing that at some point becomes too large that it's more favorable to create a new pair particle-antiparticle. And this process is known as string breaking. And that's basically the reason why we haven't seen a quark as an isolated particle in experiments. And finally, another example is that of dynamical quantum phase transitions, which manifest themselves in the form of non-analyticities that occur as a function of time in the quantum many-body dynamics. And what is common to most of these examples is the fact that there's been an increased interest in the study of such processes, and that's been driven by all the recent progress that has been done in quantum simulation or quantum simulator techniques. And I think that right now we are at a very privileged moment where we can access a really high level of control at manipulating such systems at the quantum level. So here I'm showing you a couple of examples of some beautiful experiments. In particular, these two have to do with dynamics of quantum systems, and it's dynamics in two-dimensional settings. So for example, in the experiment on the left-hand side, it's an experiment about many-body localization, like I said, in a two-dimensional system. While on the right-hand side is an experiment where they study transport properties. When I remember correctly, it's a Fermi-Hobart model in the presence of a tilted external potential. And they even relate the physics of this experiment to that of fractonic systems, which are also quite fashionable at the moment in condensed matter, in the condensed matter community. And finally, in this third experiment, well, this is not about dynamics, but I wanted to show you like the possibilities for arranging these kind of systems that we can now can be done kind of easily in the lab, or relatively easily. So from that perspective, one might ask, well, what about the theoretical methods? And it is also true that there has been a lot of progress over the past decades, in particular for one-dimensional systems. Now we know that tensor network-based algorithms are a good option to use. In particular, we are dealing with quantum states with relatively low entanglement or moderate entanglement. On the other hand, if you go to higher dimensions, then one can use a dynamical mean field theoretical approximation, which actually becomes exact in these limits. But there is still a huge gap in between, in particular in 2 and 3 dimensions, which of course are of interest. And so here I'm putting a big question mark to indicate that there is still plenty of room for improvement, even though there's been already a few remarkable advances also in this direction. And what I want to show you today is a little attempt at eventually get rid of this question mark. So of course, the difficulty of the problem, and this is in general for any dimension, is that if we want to study the coherent quantum dynamics of a many-body system, what we need to do is to solve the time-dependent Schrödinger equation. And like probably this you all know very well, the computational cost required to find a numerically exact solution in general grows with the number of degrees of freedom. And you can see that, for example, if you express the quantum state in terms of a computational basis, and let's consider for the moment, let's say a system of n spin 1/2 particles. So then you know that here you would need to compute and store 2 to the n of these amplitudes, which kind of encode all the information about the quantum state. So this is the kind of exponential complexity that I'm talking about here. And there are a few approaches on how to solve this problem. And the one that I will present today is based on this picture, which says that instead of having to store and having to compute and store all of these 2 to the n amplitudes, for example, we just generate them on the fly. And to do that, you would need a machine that is capable of doing this task. So of generating the corresponding wave function amplitude, or a good approximation of it, given as an input, let's say a spin configuration. And examples of these kind of machines have been already introduced, like in particular in this paper from 2017, Carleo and Troya used a particular kind of artificial neural networks as this machine to perform the task that I just described, which is that of solving the quantum many-body dynamics. And what I want to show you today is another type of machine that we call variational classical networks. But as I will argue, these are also kind of similar in some sense to these artificial neural networks, although with kind of different approach in how to build them. And so let me already switch to the method of variational classical networks. You can find more details of it in this publication. So actually, these classical networks were introduced a couple of years ago by two of my collaborators, Markus Schmidt and Markus Heil. However, they built what is known as perturbative classical networks. And what I want to show you today is an improvement on these perturbative classical networks. Nevertheless, the general approach is the same, so I will start with these perturbative classical networks. So the general idea that we have in mind is that we want to describe a family of Hamiltonians which have this form. So there is a diagonal part in a given basis, let's say the computational basis of spin configurations. And then there is off-diagonal part, which you can think of as some perturbation. Now, the formal solution to Schrödinger's equation, it's given by this expression, where you apply the unitary time evolution operator onto the initial condition. But like I said before, you can always expand this vector or this state in a given basis. And what we do now is that we go to the interaction picture, where the time evolution operator can be written in this manner, where these E of S are the eigenvalues of this Hamiltonian H0. So this we can compute. And this W of T, it's basically given by the time order exponential of the time integrals of the perturbation. So now we plug this expression back in here, and we take, or we form the brackets with one of these vectors so that we can isolate this amplitude. And what we find is given here. So what we find is that this amplitude will be given by the exponential of these eigenvalues. And like I said, these we can compute easily. And now we want to compute, or we have to compute this expectation value. And this is in principle not so easy, but there are, however, a few possible solutions. One of them is given by the cumulant expansion. I think it was first introduced by Kubo in 1962. And basically here I'm just giving you the result of doing this cumulant expansion, which is some sort of more sophisticated perturbation theory. In any case, by applying this cumulant expansion, we have managed to write the wave function amplitude essentially as the exponential of some function, a function of the spin variables and time. Notice that in this exponential here you have time integrals of the different cumulant averages of the perturbation, but the result will be a scalar. It will not be an operator. So after all, here you will have a complex value function that only depends on the spin variables and time. And I will show you later, you can think of this function as some sort of effective classical Hamiltonian. And in general, you can write it in this manner, where the different terms here correspond to the different terms in the cumulant expansion. So this is the 0th order correction, the 1st order correction, and so on. And it turns out that for many cases, you can write these functions in this manner, where you have these phi of s, which are like spin-spin interaction terms. They are local and they satisfy the symmetries of the system. And then they are multiplied by a complex coupling. So overall, this classical Hamiltonian will be complex in general, and therefore this amplitude will be correspondingly also complex in general. And let me just show you an example to make this a little bit more concrete and not too abstract. And the example that I'm showing here is that of a transverse field Ising model, which has this Hamiltonian. So in the settings that I was describing before, the H naught would be the sigma z, which is obviously diagonal in the basis of eigenvectors of sigma z. And then the perturbation is the transverse field. Okay. So if you do the prescription, if you follow the prescription that I just told you about, you would find that for the one-dimensional transverse field Ising model, the first order effective Hamiltonian has this form. And you see it has exactly the structure that I described before. It has some couplings whose expression is given here. And these couplings multiply some spin-spin terms. So for example, here you have nearest neighbor interaction, and this is next to nearest neighbor interaction. But importantly, these are all sigma sets. So it's really a classical Hamiltonian or it's if you want, a diagonal Hamiltonian. So that's why the method it has the word classical, because it's described by a classical Hamiltonian in some sense. And now these are also called networks because you can always kind of seeing these effective systems as a network where the nodes are the spins represented here by black dots. And then the connectivity in the network is basically determined by the couplings. So this is, for example, the local structure of the network for the two-dimensional transverse field Ising model. So you see that you have, like, for example, this coupling here is nearest neighbor, which would be this C1, and then you have next to nearest neighbor, which is this coupling here. And in 2 dimensions, you have also products of 4 spins. So for example, the red coupling is the product of the 4 spins around the central one. And you have also the patch of 3 of these spins and the central one, which are the orange lines here. Okay, so what I've described so far is what is known as perturbative classical networks. And like I said, these were introduced in this paper. And now the idea or the main motivation for this work was to think whether we could do better than these networks. And of course, I haven't shown you any results, but I will do in a moment. And that's what we did in this work. And
Roberto.
Yes?
Roberto, could you go back just to the previous one? I kind of got lost with the... So what are the S exactly in there?
Right, these are spin variables.
Right, so can you go back to the previous one?
Yes.
Just to see what is the correspondence.
Right, exactly. So the Hamiltonian that I was writing there, like
right.
This Hamiltonian, which actually you can see that's simply a classical Ising model with nearest neighbor interaction and next to nearest neighbor interaction. In this case, this Hamiltonian is what I wrote here generally as this effective Hamiltonian. And actually, in the next slide, I just wrote the first order correction. So up to this part here.
Yeah.
And then you would compute like the corresponding, or you would generate the corresponding wave function amplitudes basically using this expression here.
Right. Okay.
Is that clear?
Yeah. Yeah, I think it's
Okay,
right. Okay.
good. So like I was saying, this describes what is known as perturbative classical networks, and now we want to somehow improve them. And I will show you that what we are doing here, it really improves the method. And the way to do that is to promote the perturbative classical networks to variational classical networks. So basically the idea is that we keep the structure of the network that is given by the Cumulon expansion. So let me go back here. So for example, for the transverse Phi model, the structure of the network would be as given here for a two-dimensional system. But in general, we keep the structure that is given by the Cumulon expansion, that is generally written as this in the form of this effective Hamiltonian. But now, instead of keeping the couplings that are also given by the Cumulon expansion, we replace them by variational parameters, which we then optimize using some variational Monte Carlo. That in the context of quantum dynamics, it's also known as time-dependent variational principle. So that's the basic idea. We use basically all the machinery that I already showed you on how to build this kind of effective classical Hamiltonians. But now we do, on top of that, we do a variational optimization for these couplings. And as I will show you, that improves significantly like the accuracy and the method overall. So like I said, the resulting networks are optimized doing some form of variational Monte Carlo, which in this case is known as time-dependent variational principle. And I don't want to spend too much time on this slide since it's a little bit technical, but you can find the details in these two papers. In particular, in the appendix of this paper, you can see a very clear derivation of these equations. Let me just say that the main idea of the time-dependent variational principle is to map the time-dependent Schrödinger equation into a system of nonlinear first-order differential equations that describe the evolution of the variational parameters. So here I'm denoting by eta the set of variational parameters in your wave function. And the way to choose the variational parameters so that this object describes the time-evolved quantum state, it's by solving this equation here. But like I said, the essence of this equation is that it allows you to map the quantum dynamics into the ordinary differential equations that govern the evolution of these parameters. So I will move forward, but if you have questions on this, I can come back later on.
Roberto?
Yes?
Sorry. So the variation principle is the eta you are talking about. So its dimension is to the k. So how is the dimension size determined? Why it is related to how many parameters you need to fit?
How many parameters do I need to fit?
Yeah.
That's the question. Yeah, that really depends on basically the order of the Cumulon expansion. So for example, here, for this case of the transverse Phi model, if you take a first order network, it will be given by this expression. And basically here you would need only 3 parameters, which would be like eta 0, eta 1, and eta 2. And this is the case for a translational invariant system. Okay. So normally you would like to go to higher orders because, like I will show you, you can systematically improve the convergence of the methods if you go to higher orders. And then the number number of variational parameters will grow, but in any case, it's not, it's like a relatively low number of variational parameters that you need to optimize, but that really depends on the model that you are studying and to which order you want to go in the Qumran expansion.
I see. Thanks.
Mm-hmm.
I have a questions.
Yeah.
Can you go back? Yes, this is that. And so basically, you want to see how this eta evolve. And so you solve this differential equation by inverse matrix or by differential solver or something else.
Yeah, it can be a little bit tricky actually, because this matrix here is actually not invertible. So you need to take what is known as a self-inverse. And that actually can lead to some numerical instabilities. So it's a little bit tricky. And in particular, like if you see like this original paper, they managed to do, in these two papers, they do it with artificial neural networks, which are a little bit more complicated than the networks I'm presenting today. But if you look at this paper, like the first paper, you see that they managed to do like quantum dynamics for really short times. And in this second paper, they kind of explain some of the numerical instabilities that you find by actually solving this equation. So it's like I said, it's a little bit tricky, but there are ways to do it.
Okay. So my second question is: have you ever used another variation principle like a Dirac-Frankel variation principle, and the another one is called maybe Maran variation principle? I think there are 3 variation principles I hear before.
I think this is actually, or I don't know if it's exactly the Dirac variational principle, but it should be equivalent in any case. As far as I remember, people also refer to this equation like the Dirac-Franklin, I think, variational principle.
Okay. Thank you.
Yes. Right. So I will also skip this slide. The only thing to know about it is that with these networks, which maybe let me show you one more time, which with these networks that you write as the exponential of this classical Hamiltonian, you can sample observables and study the time evolution of observables basically by recasting this expression as some sort of a statistical average with this kind of Boltzmann-like factor, which has to do with the real part of this effective Hamiltonian, which in general is complex. All right, but in short, like what I wanted to say is that you can sample observables quite easily by doing classical Monte Carlo. Right, so now I will show you a few results. And this is for the one-dimensional transverse field Ising model. So this is more like a benchmark of the methods. And so the Hamiltonian, again, it's given here. You have a sigma set Ising interaction, and then you have a transverse field. Now the reference Hamiltonian, or like the diagonal part of the Hamiltonian, is the sigma set. And the perturbation, again, is the transverse field. And what I will consider is this kind of initial state, which is simply a equal weight superposition over all spin configurations. So here you are like really deep into the paramagnetic phase of the model. And then, of course, like this is the initial state, but then we want to study the unitary dynamics generated by this Hamiltonian. So again, like I followed the prescription that I told you about using the Qumran expansion. And these are, for example, the effective classical Hamiltonians that one gets, like up to first order correction, you get, as before, classical Ising model with nearest neighbor interaction and next to nearest neighbor interaction. Now, if you take into account second order corrections, then you have like the second nearest neighbor interaction and a patch of 4 spins. So let's say that if you take these two orders, the local structure of your network would look like this. So these couplings is like the nearest neighbor, then you have next to nearest neighbor, the second nearest neighbor, and then the patch with 4 spins. And like a general feature of these networks is that if you want to go to higher order terms, basically you will generate like longer range couplings, all of them satisfying the symmetries of the problem. So you see that one can systematically and kind of easily generalize for higher order terms, but as well, you might just solve the cumulant expansion and see what are the terms that come out of it. Okay, so here are a few results. So here I'm showing you the transverse magnetization when we do the unitary dynamics. Like you might know, the one-dimensional transverse field Ising model is exactly solvable. So in this case, we have access to the exact solution, which is the black curve. And what I wanted to show you in this plot is that the variational classical networks that I'm presenting today really improve over the perturbative classical networks, as you can see here. So the variational solution is always closer to the exact solution for all the times that we studied here, while the perturbative classical networks at some point, you know, they don't go back to the exact solution, or they are like further away. On this plot, yeah, I'm aware that it's a little bit too much of information in this plot, but essentially, if you would look carefully at it, you would see that by increasing the order of the cumulant expansion, which is basically this parameter here. So here we go, for example, up to 11 order for this Ising model. You would find that you systematically converge to the exact solution. So this shows you that you can like improve the accuracy of the method in a controlled manner by adding higher order terms in the cumulant expansion. And finally, here we see the propagation of quantum correlations. So this is a space-time kind of diagram. And here we are plotting the correlations at a different distance with respect to a given spin. So here, this is the exact solution. We see that, you know, there is this kind of light cone structure in the correlations. And here, these 3 panels show you the results with classical networks with different orders in the cumulant expansion, which is basically this parameter. So you see that as you increase the order in the cumulant expansion, you are able to account for this spreading of quantum correlations better. So that's also kind of a general feature of the method, which in a way is related to, so for example, in artificial neural networks, the analogy would be to increase the number of, you know, hidden neurons, which increase the expressibility of the networks. In this case, to increase the expressibility of the expression power of the network, you need to increase the order of the cumulant expansion. Good. So now I will show you an application to slightly, well, actually a much more complicated model in 2 dimensions. But probably this is a good moment to stop if there are any questions about the first part of the talk.
So I was wondering, with this example of the spin chain, so when you write the expansion, like, is there any insight? Because I noticed, so you have nearest neighbor interactions, and then when you expand, you get these terms like, for example, the interactions with 4 spins, right, in the C4.
Right.
So
Yeah.
is there any insight, like, is that telling you something about how interactions spread or something like that? Like, I don't know. For example, the C's, C naught, C1, C2,
Mm-hmm.
like, I don't know, can you know something from knowing those C's, for example, or? I don't.
Yeah, like basically it's kind of related to this plot here. So for example, in this left-hand side panel, the network that we consider is basically this network only. So it only contains nearest neighbor and next to nearest neighbor in this classical Hamiltonian. And like you can see here, it only accounts for correlations or interactions up to a very short distance in the quantum model. Now, if you include more of these terms in the classical network, then you observe that eventually you can describe more how these correlations, these quantum correlations, propagate in the system.
Right.
And basically, well, like you see that as you go to higher orders in this cumulant expansion, you will get longer range kind of interactions in the classical system, and also like higher number of spins interacting all together. So that in a way allows you to account for more of the quantum interactions or the interactions in the quantum model.
Right. So in the numerics, essentially, what you had to do is to compute these the C terms, I guess, or.
Yeah, right. So in the numerics, what we do is to solve this equation, and like this matrix and this vector. For that, we need to sample some observables, and we sample those with Monte Carlo methods. So in the numerics, we need to solve this equation at every time step, and then like we also sample observables like the observables that I'm showing you in the plots, also by doing some Monte Carlo.
Yeah. Okay.
Mm-hmm.
All right. Thanks.
Good. So now I will move to the second part of the talk, where I will apply this method of variational classical networks to study the non-equilibrium dynamics in a two-dimensional lattice gauge theory. And like I will show you, this model actually exhibits what is known as disorder-free localization, which is some sort of non-ergodic behavior. So let me start by saying a few words about lattice gauge theory. Like in general, gauge theories are field theories, which, you know, they have like the defining feature that they are invariant on their local gauge symmetry transformations. And such local symmetry transformations are generated by a gauge group, which can be abelian, meaning that the generators of the symmetries commute with each other. And an example of that is quantum electrodynamics, which is described by a gauge theory with the U1 gauge group. And they can also be non-abelian, meaning that some of the generators do not mutually commute. And an example is that of quantum chromodynamics, which is, again, described by a gauge theory with the SU3 gauge group. So in the following, I will just concentrate on abelian lattice gauge theories. And actually, I will concentrate on a gauge theory with a U1 gauge group. So in a sense, like the theory that I will show you in the next slide, it's kind of related to quantum electrodynamics in the lattice. Now, gauge theories are normally, related to high energy physics. And of course, they are very much important in high energy physics, in particular, like within the framework of the standard model. Basically, all fundamental interactions are described by gauge theories. But it's also true that gauge theories are important for other fields like condensed matter and quantum information. So here, as I understand, like the background might be more related to quantum information. I'm putting a couple of references here, in particular, like Kitayev's toric code. It's actually an example of a set2 lattice gauge theory. Right. So now, like the type of gauge theories that I will consider are defined on the lattice, and this was introduced in the 1970s by basically in these works, like Wilson and Polyakov did it for like in the context of high energy physics, but also Wegener introduced like some Ising lattice gauge theories a bit earlier with a different motivation. In any case, these theories are defined on a lattice. In principle, it can be any lattice and it can be any dimension. I will consider square lattices. And in general, what one does is to define matter fields on the sides, and gauge fields are defined on the links of the lattice. So for a two-dimensional lattice, then you would have, for example, electric fluxes on the links, and also the gauge fields are also defined on the links. Now, let me show you concretely the model that I will consider, which is called the quantum link model. And like I said, I will consider it in two spatial dimensions. So this model is defined on a square lattice. And so first of all, is only a pure gauge theory, meaning that there are no matter fields, only gauge fields. And the gauge fields are, like in this model, they are represented by a spin 1/2 degrees of freedom, which are defined on the links. Okay. So for example, these arrows here will represent such degrees of freedom. And for this picture, we are using this convention that arrows pointing up or right correspond to spin up, and arrows pointing down or left correspond to spin down. And the Hamiltonian of the model, it's given here. It has two terms. So this second term, you can think of it as some kinetic energy. And what it does is to flip a plaquette whenever the configuration of these arrows forms a closed loop. Like in this example here, you see that the arrows are forming a clockwise loop. And then by applying this operator, you will flip or reverse the direction of the arrows. Okay. And if the plaquette, it's kind of frustrated in the sense that it doesn't form a closed loop, like in this example, where this spin is, it's like avoiding to have a closed loop, then this operator will do nothing on that plaquette. The second term, or like the first term here, it's more like a potential energy that acts also on plaquettes, and it will flip a plaquette forth and back. So in the end, it does nothing but just counts the number of flippable plaquettes that you have. So this is like the Hamiltonian, and like in the settings that I described before, like the diagonal part would be this potential energy, and then the perturbation would be this plaquette flipping term here. All right, and just like a little bit of background about this model, like I said, it's kind of related to lattice quantum electrodynamics, but with gauge fields or gauge degrees of freedom represented by spin 1/2. And it turns out that it's also quite important in condensed matter, as it's kind of related to quantum spin liquids, and in particular the quantum dimer model. So the quantum dimer model is actually a particular case of this Hamiltonian here. Okay, now this is also a little bit of kind of introduction to these gauge theories, which, like I said, are defined by the fact that they are invariant on their local symmetry transformations. And in particular, for this model, the generators of those local transformations are given by this operator. So you have one of these operator at each lattice side, which here I call R. And basically what you have on the right-hand side, it's like the lattice version of divergence of electric field. So what this term does is it counts the number of fluxes that stick out of this vertex and subtracts the number of fluxes that come in. So if you look at one of these sides, then you will count the number of fluxes going out and subtract the number of fluxes that are coming in. So like I said, this is a kind of divergence of electric field at an operator level in the lattice. Now, since these are generators of symmetries, they commute with the Hamiltonian. And also, since we are considering an abelian gauge theory, they commute with each other. And this has a series of consequences, like very basic ones. It's basically things that we know from quantum mechanics 101, namely that since these guys commute with the Hamiltonian, it means that you will have an extensive number of conserved quantities, because you have one of these operators for each lattice side. Nonetheless, this extensive number of conservation laws is less than the number of degrees of freedom in the system. Also, the Hamiltonian can be written in a block diagonal form, which is somehow related to what is known now as Hilbert space fragmentation in the quantum many-body community. And finally, one can label the eigenstates of the Hamiltonian by using the eigenvalues of these operators. And in particular, for this model, the eigenvalues of these operators are given by these integers that actually one can give the physical meaning of background charges. So if one writes the eigenvalue problem for this operator, then we see that basically these eigenvalues can be interpreted as background charges, in the sense that here you have like the divergence of the electric field, and on this side you have some sort of charge, and that's a kind of generalized Gauss law. In the case in which you would have dynamical matter fields, here you would have to add the corresponding charge density, but in this case we don't have it. And this generalized Gauss law also defines what is known as superselection sectors, which are like the different blocks in the Hamiltonian that are characterized by a given configuration of these eigenvalues. Okay. Now, we wanted to study the non-equilibrium dynamics of this model. So here, again, I'm showing you results where we start from this initial state, which is equal wave superposition of all spins. And in the language of, these lattice gauge theories, is actually a superposition over all superselection sectors. So here, I'm showing you results with these classical networks for a huge system of 80 by 80 plaquettes. And here we computed like the correlation function at different distances, which are this d, and on this axis you have time. So what we observe is that by doing this kind of quantum quench, correlations build up to rather short distances. And in a way, this is not what you would expect it, since the model that we are considering here is, a kind of generic interacting quantum model, in which case you would expect to see more like a light cone structure of correlations. So correlations will spread ballistically, at least until, at least before some sort of hydrodynamical description applies. But rather what we observe is that correlations only build up significantly up to rather short distances. And as I will argue, this is some sort of non-ergodic behavior, and the mechanism behind is known as disordered free localization. So let me use the last 2 minutes to discuss this disordered free localization. So basically the idea is that since in a lattice gauge theory, you have this set of conservation laws, which are due to gauge invariance, the Hamiltonian can be written as in a block diagonal way, where again, each of these blocks are the superselection sectors that are characterized by the set of eigenvalues of the generators. And importantly, these sectors are not connected in the dynamics, so they do not mix. That means that if you apply the unitary time evolution operator to, let's say, one of the eigenstates corresponding to a given block, then the evolution is only driven by the corresponding block. So in particular, if you start from superposition over many of these sectors, then you can write the expectation value of a diagonal observable in this manner, where basically you sum over different sectors. Like here, like schematically, I only draw 4 of them, but in general, for a large system, you will have an extensive number of these sectors. So this is really like some sort of average over these superselection sectors, which are characterized by a random distribution of these static charges. So let me maybe be a bit clearer here. Like, for example, here, these red and blue dots are the static background charges, which are the eigenvalues of these operators. So a set of configuration like this will correspond to one of those superselection sectors, one of these blocks, but you have many of them. So essentially here, you would have some sort of average over random distributions of these background charges, and that acts effectively as a disorder average. So this quantity here can exhibit some localization behavior in analogy to Anderson localization or many-body localization. So here, finally, we look again at the dynamics computed with the classical networks, and we distinguish 2 types of dynamical behavior. So here we consider this initial condition, which is a superposition over all superselection sectors, which corresponds to the case I just described. And we prepare the system such that it has an initial line defect sitting at the first column. And basically what we do here is to study how that defect travels in the system. So in this case, we see that it travels for a short distance, and then it drastically, its transport is drastically suppressed. While on the lower panel, we study the dynamics just in a given sector. And what we see here is that such defect actually travels ballistically in the system, which is more like the ergodic type of behavior that you would expect. So this already shows you that you can have 2 types of dynamical behavior, one in which you have this localization, and another where you have kind of ergodic dynamics.
Sorry, what's your D here? So why you say it is spreading or transferring? What's the D here and lambda T?
Yeah, sorry. Thanks for the question. So D is the it refers to the columns in the system. So we are thinking of this kind of square lattices. Let's say that we prepare like the initial defect on this column, and then we study how it travels at different distances, which are the different columns in the square lattice. And lambda T is simply time. So everything is measured in units of this lambda, which is, this unit of energy. So this is like the unit of energy that we take. Right, so this is time versus space. Good. And of course, like, if you would just use these methods, you cannot draw like very generic conclusions whether this is really non-ergodic behavior or is simply slow dynamics, because for that you would need to go to longer time scales, which are not accessible. However, we use some kind of complementary approach to really determine that this is non-ergodic behavior, and that relies on a percolation argument or a percolation theory. So here I'm showing you a typical superselection sector with some distribution of background charges. And basically what we find is that the effect of these background charges can be such that it constrains a lot the dynamics of the system. So essentially what it happens is that there will be some clusters that will be evolving in time, but a large portion of the system will remain like static, essentially, due to these background charges, which are a consequence of, gauge invariance. So the fact that you have this formation of small clusters, it's somehow related to the lack of ergodicity in the system. So these clusters are kinetically disconnected with each other. And we study that as a function of some parameter that basically connects the two dynamical regimes that I'm showing you here. So we go from this dynamical regime to this one in terms of this percolation problem. So in the localized side, basically what we find is that you have a lot of these small islands, but they are disconnected with each other. So the percolation probability in this case is 0. Okay. On the other hand, in the ergodic side of the transition, you observe that there is basically a big cluster that emerges, and therefore here the percolation is equal to 1. But here, as we can see, this actually kind of describes a percolation transition. So this allows us to, be more confident that what we are seeing in the quantum dynamics is really two distinct dynamical phases. One that is non-ergodic, and where presumably the source of non-ergodicity is this disorder-free localization, and another phase which is ergodic, and where in this classical percolation corresponds to having a percolating system.
Sorry, what is alpha here?
Yeah, this parameter connects these two initial states. So precisely,
I can
connect them in this way. So I can give you more details, but that's what it does. You can go continuously from this initial state to this one here. Right. So since I'm running out of time, here are the conclusions. I showing you the method of I show you the method of variational classical networks, which is a promising tool for quantum dynamics, not only in one-dimensional systems, but also in 2 dimensions, like I show you for this quantum link model. In general, it has a moderate computational cost. And importantly, it has a control character that comes from the perturbative structure of the Qumran expansion. And like I showed you, we already use it to study this non-ergodic behavior in a two-dimensional lattice gauge theory. And the method has, of course, some limitations. One of it is that it has to be close to a classical limit, the H naught in the previous examples, meaning that if you increase the strength of the perturbation, then the method works, not as well as if you have a small parameter in the problem. And there are other kind of problematic situations. For example, if you have resonant processes, then they can be secular terms that will lead to a breakdown after some characteristic time scale. And also some initial conditions are problematic for the methods. But with that, I want to thank you for your attention.
Thank you, Roberto.
Thank you.
Right. So I'm happy to take questions if there are any.
Maybe I have a question. Roberto, can you go back to the Planck diagonalized Hamiltonian? So the Hamiltonian is Planck diagonalized in eigenbases, right? So each eigenbasis corresponding to different charge sector. And then how's the wave function look like? Are they all localized, or are they some range of spin configuration for each eigenvalue, for each eigenvector?
Right. So let me think.
Because I'm curious about how's the charge eigensector looks like. Are they localized, or are they spreading over the lattice?
Right. Actually, we didn't look at that, and it's true that it becomes a block diagonal, but this is using the these blocks are characterized basically by the quantum numbers of these generators, because they commute with the Hamiltonian. So it's really the eigenvalues of these generators, not those of the Hamiltonian. That's one thing. And then, in short, for your question, we didn't look at the wave function, because it's again the problem that I was telling you before, at the beginning of the talk, that for that you will need to compute and store all the amplitudes of the wave function, and that's precisely what we don't want to do with these methods. So what we want to do is to generate the amplitudes just as we need it on the fly. So for example, to sample observables doing Monte Carlo. So yeah, in short, you don't have access to the full wave function by using that method, but that's precisely the point.
I see. So the point is that the Hamiltonian do not commute with the charge sector, right? I mean, the generator of the local symmetry. They do not commute.
No, they commute.
They commute.
Yeah. And then these sectors that I'm talking about are characterized by basically the eigenvalues of these operators. Yeah.
Oh, okay. They commute, but the generator have finer symmetry, so they can be further Planck diagonalized. Then how do these localization arise? I mean, why there are so many mixture of these different sectors? Do you have a more intuition to say this?
It's really this kind of process here that if you start from initial state that involves many of these sectors, then when you write the expectation value for an observable, it's basically an average over different random sectors. So essentially, it's really like a different distribution of these charges. And that, in some sense, acts as an effective disorder in the model. So, for example, in this paper here, they discuss this mechanism in a one-dimensional gauge theory. And in that case, in one dimension, you can like work out more like the analytical expressions, and they actually show that like a concrete example of this HQ, where you can see that really the Hamiltonian depends on the super selection sectors. So it's really like if you were working in one of these models with disorder, but in this case, we don't have any disorder. It's just like you are sampling over different super selection sectors. And that's like sampling over different random charge distribution. But that's an important remark. In this case, we don't have any type of disorder. Like the Hamiltonian and the initial condition are homogeneous. So this is just an effective kind of disorder that emerges.
So your initial wave function is homogeneous, you choose?
It's homogeneous, yes.
Okay, I see.
So like this one here, which is
see.
simply a superposition over super selection sectors.
Okay. Sorry, I may have further question about the simulation. So why you say it's a network? Why you use the terminology network?
Yeah, it's like I was explaining for the IC model is basically because you can always visualize these classical Hamiltonians as a network, and that's kind of the same for artificial neural networks. Like if you go, for example, to this paper where they use an artificial neural network, they concentrate on a network that is called restricted Boltzmann machine, which again is a classical Ising model. Okay, but
the part I know, but you are not using neural network, right? You are using Monte Carlo.
Exactly. So these are not neural networks, although in fact in this paper they show that there is an exact mapping between this type of networks and for example restricted Boltzmann machines. So in that sense they are connected, and like I said, simply here you can visualize this model as a graph where the spins are the nodes of the network, and then the connectivity, like shown here, it's given by these couplings. So
I see. So in your simulation, can you handle a periodic system or it's finite size network?
Yeah, it's like, of course, like you know, in this cumulant expansion, in principle, you can go to any order that you like, provided that you have the computational resources for that. But in practice, of course, you want to truncate it at some point. So yeah, it's finite size, and like for example here, I didn't understand the part of periodicity, but like here we consider periodic boundary conditions, for example, and with that you can reduce the number of variational parameters, basically by accounting for translational the translational symmetry.
Okay, I see. Okay, thanks.
Mm-hmm.
Any other questions?
Sorry,
Well,
I may have other questions. Quick question. In Monte Carlo, how do you get all those different parameters, the variation parameters? You sample all these spin variable, and then you count all those variables expectation, and then do the differential equation calculation. Is that right?
Yeah, that's basically the idea. So essentially, what you want to do is to solve this differential equation at each time step to know what's the how to update these variational parameters in the wave function. But for that, you need to sample some observables like this local energy or these derivatives of the wave function, and like these brackets here are really averages with respect to this wave function. So you do Monte Carlo, for example, by single spin flips. Yeah, like any standard classical Monte Carlo to sample these observables. And once you have computed these expectation values, then you can solve this equation, and that allows you to update the wave function. So you do Monte Carlo both to solve this equation and also to sample observables of interest like magnetization or correlation functions and so on.
Okay, I understand. Thank you very much.
Mm-hmm.
So I just have a question about the last bit about the correlations in the lattice, like not spreading, kind of like a light cone. Is that so? So that is only within this model, I guess. Yeah. So in this bit. Okay. So is this because of this? So this S set not. So these are observables, spin observables, or?
Yeah, right. So yeah, maybe it's a little bit too much information since I was discussing lattice gauge theories, but in principle, you can also think of this model here as a spin system, since all the degrees of freedom are spin 1/2. So basically, in that plot, I'm showing you, say, the correlation of reference spin with other spins at different distances. Like, for example, the correlation between this spin and this one, and then this and this, and so on and so forth. So that's this kind of quantity here. Yeah. And now the fact that it's localized is, well, as I was arguing, that's due to this disorder-free localization. But like, if you would study the dynamics, for example, in constrained to a single superselection sector, then within that superselection sector, you will see that it's kind of ergodic. So this is not the correlation function. This is a different quantity, but you would kind of get the same for the correlation function.
Okay.
Mm-hmm.
All right. Any more questions? If not, then thank you, Roberto, and yeah, we'll see you next week, guys. Thanks a lot.
Yes, thank you for the invitation.
Okay, thank you very much.
Thank you very much.
Thank you, Roberto.
All right. Thanks, guys. See ya.
Okay, bye.
You.
Okay, see you.